Chongqing University in Taiwan, and I'm also the member of IUC and AHG, and I'm very happy to come here to share the title of Critical Thermal Limit of Annular Along Elevation and Microclimate Gradient. And I also using the information I got from this topic and using it to predict the range shift under the warming risk. No? Oh, okay. Before I start my introduction, we should know what is thermal tolerance and how important the thermal tolerance ability is. Thermal tolerance ability is a very important physiological trait in organism. This ability is how the species can endure the temperature in the environment. If the environment temperature is above or below the critical thermal tolerance ability of the organism, maybe it cannot survive in that environment. And by knowing the species thermal tolerance ability, we can use it to explain why the species distribute like that. Like the salamander in Taiwan only distribute in the above 2,000 meters high mountain, but the anuran, the frog, they can find anywhere in Taiwan. So this might because the difference between the critical thermal maximum, the heat tolerance abilities difference between them. And by knowing the critical thermal maxima and the maximum environmental temperature, we can know the range of the warming tolerance of the species. And we can use it to predict how it will endure in the climate change. And there are many factors which will affect the organism's thermal tolerance ability. One of them is in the environment they survive in. And there are many hypotheses try to explain how the environment affect on the thermal tolerance ability of organism. One of the hypotheses called climate variability hypothesis, also known as CVH. And this hypothesis suggests that the species which survive in the greater variation habitat, like the high mountain or the high latitude area, which have a very high variation on the environmental temperature, they may have a wider temperature endurance range to let them can withstand in this habitat. Another hypothesis is Brett's hypothesis. This hypothesis aims that cold tolerance exhibit greater variability and heat tolerance along the geographic gradient. Like when the elevation comes up and the heat tolerance drops slightly than the cold tolerance. And this also, on the other word, the heat tolerance is much more stable physiological trait rather than the cold tolerance. So my study is separated into two parts. First part, I want to know the environment or individuals factors which can affect the critical thermal tolerance of the frog species, which can distribute in the very wide elevation or gradient. And I also want to use in this frog species to test in those hypotheses whether it can act on the different population of the same species. And the second part, because I know the relationship between the elevation and the critical thermal tolerance of the frog, so I also want to use that to predict the elevation and range shift of the area at the high risk of the warming. And for my research species is a very beautiful green tree frog in Taiwan, and this species can distribute from about 20 meters to 2,500 meters in elevation scale. So this is a very good model to test those hypotheses and knowing whether the environmental variation can affect the thermal tolerance ability of the organism. And why I choose frog's tadpole to use as my material is because frog is the ectotherm species, and they have a very complex life cycle. They have the aquatic tadpole, and they have the terrestrial frog adult. And as the tadpole, they cannot come out of the water. So if the water temperature is not suitable for them, they just can endure. And it's based on the oviposition of that. So this is why I chose the frog tadpole for the research species, research material. And the experiment of my first part is I choose in 9 different elevations habitat and collect the tadpole from the habitat. And I bring the tadpole back to the laboratory and I measure their body mass, their development stage, and I measure their weight, and I measure their length. And then I warming up or cooling down them in the constant rate in about 0.25 Celsius degree per minute. And when they lost the reflection, we consider that tadpole is arrived their critical thermal tolerance, including critical thermal maxima, CT max, and critical thermal minima, CT min. And the range between the critical thermal maxima and minima is the range that species could, or that population could endurance. We call that thermal breadth of the population. And then we also collected the environment temperature data by Hubble data logger for 10 days. Why I only record 10 days? It's because the tadpole is stayed in the temperate water body. So if I monitor too long, maybe it will become drought. Oh, sorry. And for each population, I collect 10 factors that may affect on the thermal tolerance of the tree frog tadpole. And then I first using PCA analysis to group each variable, and I using GOM to testing the relationship between each factor and the tadpole's critical thermal tolerance. And here comes to the second part, because in the first part, I know the relationship between the elevation and the critical thermal maxima. So first, I using MaxSense to construct the species distribution model, and then I fit the STR and elevation data into the predicted species distribution range. And then because I know the relationship between elevation and the CT max, so I use regression kriging to transfer the elevation data into the predicted CT max distribution, just like in the figure. And then I have the predicted CT max of this species in the elevation range. So I just minus the warmest temperature in the work-life biofilm layers, and I will get the warming tolerance of this species within the predicted distribution range. And I consider if the buffer range is lower than 10 Celsius degree, that population may face in the critical risk of the global warming. It's like the red area I show in the figure. Oh, and here comes to the result. For the first part, I found the CT max have significant positive correlation to both PC1 and PC4. This means when the elevation or latitude become higher or larger, and the temperature become colder, the critical thermal maxima will drop. Means they don't have that such good heat tolerance ability. And in addition, I quantified the time I collected the tadpole, and I found that if the tadpole is collected closer to summer, it will have a better heat tolerance ability rather than the closer to winter. And for CT min, it has significant positive correlation with PC1 and negative correlation with PC2. And for the PC1, the result is similar to the critical thermal maxima, but the only difference is for the CT min, the lower CT min means better cold tolerance, not the worse tolerance. Okay. And for PC4, we find that if the tadpole is larger, it can endure much colder temperature. And I also want to test whether this species, different population can fit in those two hypotheses I just talked about. And we found that the thermal breadth means the range between the critical thermal maxima and minima become higher when the elevation climbed up. And this is fit to the CVH prediction because the high elevations seems to be much more higher variation in the temperature. And for the breadth hypothesis, we find the coefficient of variation within the population of CT max is much more lower than CT min. So it means CT max is much more stable rather than the city max, rather than the city mean. Yeah. And for the second part, currently there are about 29.57% of the potential habitat of these tree frog species are under the high warming risk. And the highest boundary of this high-risk range is about 483 meters. But under the worst greenhouse emission scenario, in about 2061 to 2080 years, this range will climb up to about 65.44%. And the highest boundary of this range is about 1,528 meters. And we also want to know if we just control the emissions, maybe the situation will become better. So I also use in the SSP 1.2-6 scenario. It's the best scenario with the greenhouse emissions and doing the same predictions. And for 2061 to 2080, this area is dropped to 47.75%, and the highest boundary is going to 755 meters. So, and for the conclusion of my research, for the first part, I find that critical thermal tolerance decreased within the increase in elevation, and both two hypotheses can apply in the single species but different population in different geographic gradient. And for the second part, we found that low elevation population facing a higher risk of climate change, although they have a better heat tolerance ability, but the low elevation habitat is too hot for them. And by controlling the green gas emission, we can slow down the expansion of the high warming risk area. And I have to thank to my PI, Professor Minfeng Zhang, and my co-author, Dr. Desiree Anderson and Paul Pitana, and all the lab member assistant. And I also want to thank the IES give me the chance to share about my research. Thanks for listening.
Thank you, Martin. Any questions? We still have our soon.
Oh, thank you very much for your presentation. You provide so many useful, insightful information, at least to me. So what I'm curious about the highest boundary, highest limit. From the result, we saw the when we compare the low emission to the high emission, the result show that the high emission scenario have higher area.
Yeah.
From the near term, and when we compare from the near term to the far term, the far term also show higher area.
Yeah.
So I wonder this increasing is a linear increasing, or the model can have some physical constraint. Because if we continue consider far in the future, we continue consider the higher emission scenario, it may be extend to the hot area. Yeah. Do you have any physical constraint in this case?
Because I only using 2 time periods prediction, so I cannot answer you is linear or not. But for the wait a second.
One more.
For this result, we find that under SSE 1.2-7, the area range is quite smaller than the under SSP 5.8-5, right? But if you not using the 2061 to 2080, if you using 2041 to 2060, it looks very similar. It means for even we control the greenhouse gas emission until 2041, the range shift is totally the same in different scenario, but it will become different in the area from 2060 to 2080s. So this, I say it's not linear.
Can I share with you get information? Yes. Okay.
Are you using the water temperature or air temperature? It's a water.
We use air temperature. This is a good question because we don't have a good predicted water temperature, and there are many factors will affect the water temperature, like the dip or like the wind upon the water body or the water is flowing or not. So it's quite difficult to using that to estimate the scenario between different emissions scenario. Yeah.
Yeah, I want to share with you, that during the method using the material, right?
Yeah.
The material that is not very linear. You understand that full question? If you look at, just look at it here and next slide, next slide we saw that that is green, more determine if we talk about the long periods, then you have the high area, the large area.
Yeah.
Okay, this is full. Want to ask you, do you have any constraints? The constraint for if you use the high vision, we can more of that, and the one starting the limitation from the measure.
Yeah.
Develop, yeah.
Yeah. And in addition, there are other restrictions because all the data, all the predicted data of the critical thermal maxima is from currently. Because the only thing can use to the future prediction is which is not variable within the time is elevation. Elevation won't change, but the distribution of the species will change. So for this result, I only can tell you the low elevation facing the larger risk of the global warming. I cannot tell you the range or how well the low elevation population is extinct or not. I cannot tell that. Yeah. So this is some restrict about this study.
I have a short question. Do you have any experience for amphibians collecting data like as a citizen science in your country? Do you have any experience? Like eBird for birds?
Yeah, we have. So for the maxen modeling in this study, I using about so far it's fine. I using the citizen data, so I have about 14,000 occurrence data to training my model. Yeah, training the maxen model. Yeah. So yeah, I using the citizen science.
Thank you very much.
Thank you.
We have 20 minutes for a coffee break, and we will invite all of you come back to room at 4 p.m. Thank you.